Every era of human progress has had its breakthrough tool. Fire, the wheel, the printing press, electricity, the transistor. Now we stand at the edge of something new, something stranger than fiction, yet grounded in the deepest laws of nature. A computer, not built with simple zeros and ones, but with particles that can be here and there at the same time. It doesn't just calculate, it explores. It doesn't just store information, it entangles it. It doesn't just simulate data, it simulates reality. This is quantum computing, and it's not coming someday in the distant future. It's already here. In the next several minutes, we'll decode this mind-bending technology, understand how it works, and explore the incredible ways it may soon reshape science, medicine, finance, energy, and artificial intelligence itself. For decades, classical computers have powered everything we use: phones, laptops, the internet. But now, a new kind of machine is emerging, the quantum computer, and it's built on an entirely different set of rules. At the heart of every classical computer is the bit, a simple binary switch that's either a 0 or a 1. It's like a tiny digital light switch that's always either on or off, with no in-between. Billions of these bits power our digital world. These bits flow through microscopic circuits, turning on and off to represent everything from text and images to video and sound. All your apps, emails, and websites are just patterns of bits switching at incredible speed. Quantum computers use something far more powerful than bits: qubits. A qubit isn't limited to just 0 or 1. It can exist in both states at once, thanks to a strange quantum property called superposition. Think of a spinning coin. Until it lands, it's both heads and tails. That's similar to how a qubit exists, not in a single state, but in a blend of all possible states, giving it the power to explore many outcomes simultaneously. Qubits can also become entangled, linked in such a way that the state of one instantly affects the other, even if they're miles apart. It's a deep quantum connection that defies the logic of classical physics. Quantum computers use interference to guide their calculations, boosting the probability of correct answers and canceling out the wrong ones. It's like tuning a signal to focus only on the truth. Classical computers think in straight lines, each step following another. Quantum computers, by contrast, can explore many paths at once, thanks to superposition, entanglement, and interference. It's a new way of computing entirely. This opens the door to breakthroughs in medicine, materials science, logistics, and finance. Quantum computers could simulate molecules, solve complex optimization problems, and transform industries we've barely begun to imagine. Quantum computing is still in its early days, but progress is accelerating. As researchers and engineers push the limits, we're witnessing the birth of a new era, one where the impossible becomes possible. To preserve delicate quantum states, the machines are housed in intricate dilution refrigerators. These towering, multi-layered systems use advanced shielding and cryogenic technology to isolate the qubits from external heat, sound, and even light. Inside these refrigerators, qubits are created using superconducting loops, trapped ions, or photons. These tiny quantum systems are controlled with microwave pulses, lasers, or magnetic fields to carry out operations with atomic precision. Quantum logic gates work very differently than classical ones. Instead of flipping bits, they rotate the qubit state in complex ways, described using matrices and vectors in a multidimensional mathematical space called Hilbert space. Every quantum operation must be incredibly precise. Just a small disturbance, like a stray atom or a vibration, can collapse a qubit's fragile state, turning it into a useless classical bit and corrupting the calculation. Once the quantum program runs, the qubits are measured, and their superpositions collapse into definite outcomes. Because quantum behavior is probabilistic, you don't get the same answer every time. You get a distribution of outcomes. To overcome this randomness, quantum programs are executed many times, sometimes thousands. Statistically analyzing the results reveals patterns and probabilities that point to the correct answer with confidence. Modern quantum systems are hybrids. Classical processors handle setup, control, and measurement, while quantum chips perform the core quantum logic. This pairing is essential for real-world quantum computation. Maintaining this delicate balance requires layers of cooling systems, calibration routines, and quantum error detection techniques. But even with all this complexity, today's quantum computers are already performing valuable experiments. While we are far from a fully mature quantum system, the building blocks are falling into place, and every year, researchers push the boundaries of what quantum hardware can do with greater accuracy and scalability. Quantum computers are ideal for tackling complex problems where classical methods fail, especially problems with enormous combinations or interactions that grow exponentially beyond our current capabilities. One powerful application is quantum simulation, modeling molecules, atoms, and quantum materials with incredible accuracy. This could revolutionize drug discovery, material design, and chemistry at the fundamental level. Quantum optimization is another key area, solving complex logistics problems like airline schedules or delivery routes, where the number of possible solutions explodes beyond what a classical computer can reasonably explore. Quantum computers can evaluate multiple possibilities at once using superposition and interference. Instead of trying one path at a time, they explore many in parallel, reducing years of computation to minutes. In cybersecurity, quantum poses both threats and opportunities. It could break existing encryption, but also enable quantum-safe cryptography, ensuring our data remains secure in a quantum-enabled future. Search problems that once required billions of steps can be accelerated using quantum algorithms like Grover's, which dramatically reduce the number of operations needed to find a needle in a digital haystack. Machine learning could be transformed by quantum computing. Models could train faster, manage high-dimensional data more efficiently, or simulate neural systems in ways we can't yet do with classical tools. Quantum finance is also growing, modeling risk, optimizing portfolios, and analyzing markets using quantum algorithms that understand and process uncertainty more naturally than classical systems. Early results show promise, but many applications are still in development. As quantum hardware improves, more industries will begin integrating quantum techniques into their workflows. These are just the first sparks. In time, quantum computing could unlock entirely new industries, inventions, and insights, reshaping our understanding of what's possible in science and technology. Quantum computers are based on fragile physics. The very properties that make them powerful, like superposition and entanglement, are also what make them difficult to control and scale. Qubits are easily disturbed by their surroundings. A tiny amount of heat, vibration, or electromagnetic radiation can destroy their state, what physicists call decoherence. To fight decoherence, qubits must be shielded and corrected in real time. But quantum error correction requires many physical qubits to protect a single logical one, meaning we need hundreds or thousands of qubits working in harmony. Today's machines are small and noisy. They can run short programs with limited accuracy, but they aren't yet capable of solving large, real-world problems at scale. As systems grow, complexity rises. More qubits means more control lines, more heat to manage, and more opportunities for interference, slowing progress and increasing cost. Software is another challenge. Many quantum algorithms are still in research phases, and new tools must be invented to program, debug, and optimize quantum workflows. No single hardware platform dominates yet. Some use superconducting qubits, others use trapped ions, photonics, or topological methods. Each has strengths and unsolved challenges. Quantum computers also require specialized facilities, complex cooling equipment, and highly trained teams, limiting access and raising the cost of experimentation. Still, we're moving fast. Governments, universities, and tech companies are pouring billions into solving these problems, advancing both hardware and algorithms at a rapid pace. Like the early days of classical computing, quantum is in its infancy, but we're already seeing real progress, suggesting a future where quantum becomes part of everyday innovation. Artificial intelligence is helping accelerate quantum development, automating experiments, tuning hardware, and simulating quantum behavior with machine learning. AI models can predict how qubits will behave, adjust for fluctuations, and even find the optimal parameters for error correction or qubit initialization. Quantum computing can return the favor, boosting AI by accelerating certain learning tasks, like matrix operations, clustering, or optimization problems that power modern models. Researchers are already exploring quantum neural networks, blending ideas from neuroscience, quantum physics, and machine learning into entirely new algorithms. Hybrid systems are emerging. AI runs on classical hardware, while quantum handles core computations, resulting in tools that benefit from both speed and flexibility. AI is helping solve quantum chemistry problems, discover new materials, and guide the design of next-gen quantum hardware based on past experiments. Some startups are training quantum-inspired models, algorithms that mimic quantum logic but run on classical chips, helping bridge the gap while quantum tech matures. As more quantum data becomes available, AI will play a key role in filtering, analyzing, and interpreting it, accelerating discovery across science and industry. This synergy between quantum and AI is more than a tool. It's a partnership that could redefine what it means to compute, learn, and create. We're just beginning to see what's possible. As both fields evolve, they may fuse into something radically new, a leap in both intelligence and computation. The current stage of quantum computing is called NISQ, Noisy Intermediate Scale Quantum. It means systems aren't yet perfect, but they're powerful enough to begin solving useful problems. Researchers are now mapping out which tasks today's machines can actually perform better than classical ones, a concept known as quantum advantage. This milestone is critical. It will show definitively that quantum is not just a theory, but a practical tool for solving problems that were once out of reach. To get there, we need advances in every layer, better materials, more stable qubits, improved algorithms, and scalable architectures that can grow beyond a lab demo. Startups and researchers are experimenting with error suppression, cryogenic controls, and quantum memory, all part of building a usable quantum stack. Governments are launching national quantum strategies, investing in quantum-ready infrastructure, and pushing for global leadership in this critical technology. A growing quantum workforce is forming. Engineers, scientists, and developers are being trained to work at the intersection of physics, software, and systems design. Open-source tools, quantum cloud platforms, and educational initiatives are democratizing access, so more people can build and experiment with quantum now. The path forward includes co-design, hardware and software evolving together to make quantum computing more reliable, usable, and eventually mainstream. This isn't just a new chapter, it's a whole new playbook. Quantum computing will reshape industries, accelerate science, and challenge our imagination. Quantum computing has moved from theoretical physics to real-world labs, and now it's entering classrooms, companies, and careers. This is a once-in-a-generation transformation, an opportunity to rethink how we solve problems, design systems, and understand the universe itself. You don't need a PhD to get involved. There are courses, communities, and platforms where anyone can learn, contribute, and grow. Whether you're an engineer, creative, teacher, or entrepreneur, quantum computing will eventually touch your field. The earlier you explore, the more you'll understand its impact. Learning quantum is like learning computers in the 1970s or the internet in the 90s. Those who start early will help shape its evolution. From IBM's Qiskit to Google's Cirq to Microsoft's Azure Quantum, there are tools to help you experiment with real quantum logic today. As these tools grow more powerful and accessible, a global ecosystem of builders, thinkers, and problem solvers is forming. Don't wait for permission. Dive in, ask questions, run experiments, teach others. Help move this technology forward by being part of its story. The quantum revolution won't happen overnight, but it will happen through people like you choosing to engage and lead. Welcome to the quantum era. The future is being built now, and it needs dreamers, learners, and pioneers like you. And like this video and subscribe to learn more about the fantastic world of quantum computing.